Hello there. In this unit, we are going to be looking at electrochemical reactions. And in electrochemical reactions, we're going to have electrons. They're going to be going from place to place. Electrochemical reactions take place in devices like batteries. Electrochemical reactions are what occurs when metals rust, when you burn things, when you digest stuff for the energy. All of these are electrochemical reactions where electrons are transferred from one atom to another throughout the process. So let's get started. So inside of a battery, you're going to have a chemical reaction that provides electrons at one end of the battery or one terminal and accepts electrons at the other. So that means that there's part of a chemical reaction that's giving up electrons at this side, and the other part of the chemical reaction is going to take them at the other side. When you have an electrochemical reaction like this one uses, it looks like nickel and some sort of metal hydride inside there, but you might have one that's made of zinc and copper. And you can kind of see a little better when you write out the reaction in full here. The zinc, the solid, will have no charge, just like the copper over here as a solid has no charge. The copper in this copper sulfate has a charge of +2. And the zinc in this zinc sulfate also has a charge of +2. So that meant that the zinc here ended up giving up 2 electrons to end up with this positive charge over here. So this is giving 2 electrons. And this copper here, it's going to take 2 electrons, right? So taking 2 electrons. And so as this reaction proceeds, the electrons will be transferred from the zinc to the copper in order for the reaction to occur. And so all they do in a battery is they separate the 2 halves of the reaction, make the, say the zinc side would be at this end, and then the copper would be here on the other side, the copper 2+, accepting the electrons as they go through the circuit. So of course in chemistry, as in most sciences, there will be terms to help you describe the things that are going on that you might not use in everyday life. The term here for the losing of electrons, like what happens with the zinc, is called oxidation. And the term for taking the electrons, or accepting them, is called reduction. And so you would say that the zinc here is oxidized and the copper here is reduced throughout this reaction. And together it's called a redox reaction. And all of our electrochemical reactions that we're going to learn about in this unit will be some variation of this. Okay, so some students need help in remembering these new terms because they're a bit counterintuitive, especially the reduction one. Because when you hear reduction, it sounds like there's less of something, right? Something's reducing. But it's the opposite with redox reactions, because reduction is the gaining of electrons, where oxidation is the loss. And so a couple of sayings help you remember this. One is, Leo the lion says grr. I don't know if lion's really grr, but you can use that to help you remember that Leo is loss equals oxidation. Loss equals oxidation. So there's Leo, he's the lion, he says grr, and grr is gaining electrons equals reduction. The other one is oil rig. And so it's very similar, right? So oxidation is loss and reduction is gain. And so you can use that as you will to hopefully try to keep these terms straight. Alrighty, now since every redox reaction is going to have part of the reaction that's giving up electrons and part of it that's gaining, you often are going to be separating these or looking at them as separate parts. And those separate parts we call half reactions. And so to write out the half reactions, what you want to do is show the electrons on the correct side either being given up, like in oxidation, or accepted, like with reduction. So with this one, we have the aluminum, which starts off with no charge and ending up with aluminum as being a +3 charge. So that, since that is losing electrons, that's going to be our oxidation. So we'll put it here. So we got aluminum, and it becomes aluminum +3. And so you'll add those 3 electrons on the right because those electrons are being given off by the aluminum. On the other side here, we got this copper 2+, which ends up being copper with no charge. So that means that this copper 2+ had to gain 2 electrons in order to end up with copper with no charge that is neutral. So to show the gain, you'd put it on the left. To show the loss, you'll put it on the right. Okay, so far, all the redox reactions we've looked at have either had ions or had elements. And so the charge on the ion or the element was easy to figure out. But there's a bunch of other entities that are involved in redox reactions where it's not immediately obvious. And so we use oxidation numbers to keep track of the electrons in that case. So here are the rules for assigning oxidation numbers. So the first two you already know. If you have a pure element, you're going to give it an oxidation number of 0. If you have an ion, whatever the charge of the ion is, that will be the oxidation number. In case of sodium chloride here, you've got +1 and -1. So far, so good. Now, if you ever see a hydrogen, you're going to give it an oxidation number of +1, like 90% of the time, or 95% of the time. The exception then is whenever you have a hydride, that's if it's bonded to a metal, in which case it'll have a -1 charge. So over here, this is hydrogen bonded to oxygen, so it'll get a +1 here. This one is hydrogen bonded to lithium, so that's a hydride, and so this would get a -1 charge in this case. Next is oxygen. Oxygen almost always will be -2, and its exception is the peroxide polyatomic ion, which gets a -1. So in water here, the oxygen will be a -2, and in most cases it'll be -2. But if you see this little O2 along with metal or hydrogen like this, that's a peroxide. And so what you have here is a -2 for the whole thing, but that means each oxygen is a -1. Finally, what you do is using the hydrogen and the oxygen rules that we've just done, you can deduce what the oxidation number of the remainder of a compound or polyatomic ion will be. So for example, we have sulfur dioxide here, and we know that this is oxygen, so it's going to have a -2 charge. There are 2 of them, so that makes a total of -4. And since this thing overall has no charge, that means the sulfur has to have an oxidation number of +4, so that these two balance out to overall equal 0. For our next example here, we have oxygen again, which of course has a -2 charge, or -2 oxidation number, multiplied by 3, so overall we've got -6. Now the tricky part here is that this isn't a neutral molecule, it is a polyatomic ion. So overall it's going to have a charge of -2. So you have to make the oxidation numbers add up to -2. So that means this carbon must be a +4 here, because +4 minus 6 will give you the -2. We'll do some more practice on that as we go along. Alrighty, so let's follow the rules here and see if we can assign oxidation numbers to all of these elements. So first off, we have oxygen. It's all by itself. It's a pure element. That'll be a 0. That one was easy. Next, we have nitrous oxide, or nitrogen monoxide. And so this is going to be -2 for the oxygen, which means the nitrogen must be +2, so that overall it's 0. Here we got nitrogen dioxide. This is still -2, but now there's 2 of them, so overall it's -4. So that means this nitrogen must be a +4, because overall it's still 0. Sulfate, this polyatomic ion here, oxygen's -2, 4 of them, so that makes -8. It has to equal -2 overall, so that means that the sulfur is +6. We got sodium peroxide here. So peroxide has a -1 oxidation number. There's 2 of them, so that's -2 overall. And the sodium here is an ion, so it'll have a charge of +1 and also an oxidation number as well. There's 2 of them, so that makes +2. And if we add those 2 together, overall they equal 0, which is the charge of the whole compound. Finally, good old chromate here. So potassium part is an ion, so that'll be a +1 charge. There's 2 of them, so that makes a total of +2. We've got oxygen over here, and that's a -2 charge. We've got 7 of them, so that's -14. Overall, this thing has no charge, so that means that overall we need +12 to balance out all of these. 12, sorry. to equal 0. And that means each individual chromium in here has a +6 oxidation value. Okay. Alrighty, next on our agenda is being able to use another little bit of slightly confusing language. So when you have an oxidation reaction, it is going to be losing electrons and providing them to another component that's going to take it. And so the part that's oxidizing, that is losing the electrons, is called a reducing agent because it can cause something else to be reduced. So good old zinc here, which starts at 0 and ends up with +2. This means it lost electrons. So this is an oxidation reaction. And so this thing here you would call a reducing agent because it can reduce something else by being oxidized. In this case, the thing being reduced is the copper ion here, right? And maybe I'll pick a different color. Good old blue, why not? And so here we have a reduction, which means that this guy here is an oxidizing agent. So a little tricky terminology that is littered throughout all of this electrochemistry. To keep it straight, just remember the thing that's being reduced is the oxidizing agent, and the thing that's being oxidized is the reducing agent, sort of like opposites, and you should be all right. Okay, so let's put all our skills together and see if we can identify all the different parts of this redox reaction. So we'll start with oxidation numbers. All the ions, we can just put their oxidation numbers in quickly. Potassium's a +1, chlorine is a -1. Oxygen here is an element, so it's going to be 0. Over here we have oxygen and polyatomic ions, so that'll be -2. There's 3 of them, so that makes -6. Overall, this is going to equal 0, so that means the chlorine here has to be +5. All right, so we see that the chlorine here goes from being +5 to being -1, and so that means that it is going to need to gain 6 electrons to get from +5 to -1. Think of it like a number line. And then the oxygen, which we'll do in a different color here, goes from -2 to 0. So that means that it is going to be losing electrons, 2 of them. So now we can split this up into half reactions. The chlorine here at +5 is going to need to gain 6 electrons in order to become the chlorine at the -1. And then on the other side here, we've got the oxygen at -2, and it is going to give up 2 electrons to become oxygen at 0. So over here we have gain of electrons. So this part here is the reduction. And this part here is the oxidation. And then our flipped language means that, I'll use purple here, it means chlorine here is the oxidizing agent, and the oxygen here is the reducing agent. Great! New terms and new ways of showing electrons in your half reactions. Okay, so finally, one last little wrinkle to point out to you, because you might see it as we go along through this unit, and that is that in some rare occasions, the same element can be both oxidizing agent and reducing agent. So let's have a look at this example. We've got hydrogen peroxide here, and you know that peroxides are going to have an oxidation number of -1. The hydrogen's always +1 in this example, so we can put +1s in here. It's not going to change. But on the other side, you see that the oxygen, got a regular oxygen here in water, which would be -2, and you have oxygen, the gas, which is 0, which means some of these oxygens in peroxide are going to gain electrons and become the oxygens in the water, while others of them are going to lose electrons and become the oxygens in the gas. So disproportionation reaction means that you're going to have both occurring to the same element in the same compound. So this is both oxidizing and reducing agent. So that's a disproportionation reaction. You won't see them too often, but when you do, it's nice to know about them. So there you go. Hope that helped, and we'll see you soon.